In this lesson on icing, we aim to understand the cause of aircraft icing and the dangers it poses to aircraft operations. Most importantly, we will learn how we can recognize and subsequently avoid icing conditions in the atmosphere. Firstly, let's understand why icing is so dangerous. What is the danger of airframe icing? An aircraft's wing has been designed to exacting aerodynamic standards to create lift and reduce drag. Airframe ice will affect both these factors in detrimental ways. Ice accumulation will significantly affect the shape of the airfoil, and as a result, lift will be reduced. The greater the ice accumulation, the greater the loss of lift. Ice can also disrupt the flow of air over the airframe, creating drag. More accurately though, parasite drag. This is a force which opposes the aircraft's flight path and dramatically affects the aircraft's performance. Another performance factor to consider is weight. Significant ice accretion can increase the weight of the aircraft. This may not seem so bad, but to counteract this extra weight, we need to increase lift. And as we have just stated, ice on the airframe will have the effect of reducing lift. The combination of these effects increases the stall speed of an aircraft and reduces its stability. Icing also has additional effects on aircraft instruments. It can block vents and ports, and so, in icing conditions, be wary of instruments that rely on these vents and ports for accurate readings. Additional problems can be encountered when ice develops around and over the control surfaces. If ice forms, not only can the control surface be covered, but also the gaps between the control surfaces. This leads to control jam, which is a significant hazard to a pilot. Icing is a significant hazard to aviation, and the subject needs to be thoroughly understood. Let's now examine how icing develops. Aircraft icing occurs because of the presence of supercooled water droplets in the atmosphere. Supercooled water droplets are water which is in a liquid state even though the temperature is below 0 degrees Celsius. This happens due to the absence of freezing nuclei. Freezing nuclei usually consist of particulates such as salt, dust, pollen or smoke particles. For a droplet of water to freeze, a surface or substance is needed in order to initiate the freezing process. Without it, freezing is delayed or even prevented. Supercooled water droplets can exist in the atmosphere at temperatures as low as -40 degrees Celsius. However, there is one very large surface which, when presented to the supercooled water droplets, will cause them to freeze. An aircraft. But firstly, let's understand these supercooled water droplets in a little more detail. Supercooled water droplets come in a wide variety of sizes. It is their size that controls not only the type of icing but the severity of it. The spontaneous freezing of supercooled water droplets requires a lower temperature as the droplet size decreases. In other words, smaller droplets freeze at lower temperatures than larger ones. This is simply because larger droplets are more likely to contain freezing nuclei than smaller droplets and will therefore freeze more easily. What we need to consider now is how these droplets act when they come into contact with an aircraft that is also below 0 degrees. Let's examine the small supercooled water droplets first. Since they are so small, the moment they come into contact with the leading edges of an aircraft, they will freeze instantly. As the diagram shows, through time the ice will accumulate into the airflow. In other words, forward from the leading surfaces of the aircraft. This type of icing is known as rime ice. It is characterized not only by the way it builds forward but also by its color and texture. It is opaque or milky in appearance and brittle. This is because no air is allowed to escape since the freezing process occurs so rapidly. It also has a rough sandpaper-like texture. This is because small droplets freeze straight away and accumulate to give a granular growth. It looks and feels very much like the ice that grows on the insides of domestic freezers. The large supercooled water droplets freeze in a very different way. Because of their size, they do not freeze straight away. When the droplet first strikes the leading edges of the aircraft, only that part touching the aircraft will freeze instantaneously. The remainder of the droplet can then flow backwards, slowly freezing as it comes into contact with the skin surface. When the droplet first starts to freeze, latent heat is released. This acts to keep the droplet in a liquid state for longer. Eventually, however, the whole droplet will freeze. The buildup that can be seen here is characteristic of this type of icing, called clear or glazed ice. Clear ice looks like glass and is mostly transparent, making it difficult to spot. This is because there is no air trapped inside. The freezing process is slow enough to allow the air to escape. This ice builds up in a laminar way, which increases its integral strength and makes it difficult to break and remove. On most occasions, though, it is unlikely that you will experience just one type of icing. It is far more likely that you will experience both forms. This type of icing is called mixed ice and incorporates both rime and clear ice characteristics. A third type of icing is called rain ice or freezing rain. This type of icing is the most hazardous to aircraft operations. Freezing rain occurs when rain droplets fall into an area where they become supercooled. In order for this to happen, there must be a layer of air above 0 degrees overlying a layer of air below 0 degrees. The diagram shows the cloud and rain formation within the warm layer. However, when this rain falls into the zone which has a temperature below 0 degrees, it may become supercooled. If an aircraft would fly within this area, then the airframe will be below 0. But more importantly, there are very large supercooled water droplets raining on the airframe. The rate of accumulation is so severe that within a very short time, the aircraft will not be able to sustain flight. This type of icing can occasionally be found associated with a warm front. The diagram here shows where warm air overlays air below 0 degrees. If precipitation were to fall within this area here, then it would become supercooled and rain ice should be expected. Be cautious when flying through warm fronts or occlusions, especially if the air ahead of the front is very cold. There is one more type of icing. This is called hoarfrost and is the only icing that can develop clear of cloud. This icing is identical to that which can develop on car windscreens on cold frosty nights. It can develop on an aircraft in flight or on the ground. On the ground on clear nights, when the surface temperature falls below zero, the dust and particles on the aircraft's skin can act as sublimation nuclei. Water vapor can turn directly to ice, and hoarfrost can be seen on the surface as the ice crystals are created. It is important that prior to flight, this frost be removed since it can interfere with the airflow over the aircraft. This kind of icing can be seen in flight in clear air when an aircraft rapidly climbs through an inversion. If the initial air temperature is below zero, then the skin of the aircraft will also be below 0 degrees. But when it climbs and enters the warmer air, the air traveling over the skin is cooled, and sublimation can occur, creating ice crystals and frost. This can also be observed in a rapid descent from high altitude, where the aircraft's skin temperature is still below zero. As the warmer air flows over the skin, it again can be cooled to freezing point. A clean aircraft and controlled descent will help to eliminate this type of icing. But in reality, it rarely presents a significant hazard. The final result is that the